Hello, pre-calculus students. This is Mr. Margraff. If I'm not there today, that probably means that my wife is having a baby. So, if not, though, you might just be watching this video to catch up if you are absent. So let me go ahead and get started. We're going to talk about Unit 5, Day 5. The topic is the double angle identity. Well, technically there's more than one, so we'll say double angle identities. So where do they come from? Well, they come from the sine and cosine sum and difference identities that we learned last time. So remember what those are. Let me just remind you. So I'll say recall. So sine of angle x plus minus y is sine of x. Cosine y. Let's not put parentheses around it like that. We don't have to put parentheses. And sine x, cosine y. If it's a plus, it's a plus. Minus, now they each trade. So it's like a dance. Sine dances with x while cosine dances with y. Then they trade partners. Cosine dances with x while sine dances with y. So now what if, so this is the idea behind the double angle identity. So we'll say what if we let sine of 2x is really just sine of x plus x. And what if we use our doubling or our sum and difference identity from above? So this is our first angle here, x, and this is our second angle, x. So what we're going to do is replace those with the x's and y's up here. So the formula is sine dances with x while cosine dances with x. If it's a plus, it's a plus. Now sine dances with x while cosine dances with x. So we end up getting the double angle identity here, 2 sine x cosine x. We have two of them. Here's one, and here's the other one. So 2 sine x cosine x. So now that's just a small derivation of the double angle identity. So let me give you all of them. So you've already seen sine, but let me write them in a nice orderly fashion here. So I'll say the sine double angle. So this one is, we'll make some columns, why not? So this one is sine of 2x equals 2 sine x cosine x. This one was my favorite one as a student because it almost seems like that 2 comes out in front of the sine. It's not really what's happening. You can see what's happening up here. This is really what's happening. We're just adding two different sine x, cosine x's together. But as a student, I just thought of it as the 2 coming out in front. So it's not really what's happening, but it's a good way to think about it. Okay, the other one is the cosine double angle. And there are 3 variations or 3 variants of this identity. Here it is. So cosine 2x, that's going to be the first one. The most common way to represent this is cosine squared minus sine squared. So not plus. Remember, cosine squared plus sine squared would be 1. So that's one way to represent cosine 2x. The other ways, here they are. So these are 2 other ways that we can represent cosine 2x. It's going to be 2 cosine squareds minus 1. There's one way, and here's another way. So 3 different ways that we can represent it. 1 minus 2 sine squared x. Now, the way that you get these 3 different identities is just using the Pythagorean identity. If I replace this cosine squared with a 1 minus sine squared, then that's going to give me this third identity there. If I replace that sine squared, this one right here, with a 1 minus cosine squared, it's going to give me this identity right here. So each one of those is just a variation of the first one. So this one's the most important cosine double angle identity to remember. Okay. And then the last one, this one's less common, the tangent. tangent double angle. I don't have this one memorized. I really don't. You can commit it to memory if you like. I really don't think it's going to be that helpful. If you do remember the sum identity, it's just tangent x plus tangent x over 1 minus tangent x times tangent x. So what that's going to give me is tangent 2x is equal to two tangent x's in the numerator, and then 1 minus tangent squared in the denominator. So this is just the same formula right there. So there they are. So there's a total of, let me box them, there's a total of 3 different identities. 1, 2, 3. But these variations are helpful to remember, these two right here. There really aren't any other variations on the sine, double angle, or the tangent that I know of. So there they are, 3 new identities. And we call these double angle. They're double angle because of this 2 in there. We're doubling the angle. So you can see that 2 in there. We're doubling the angle, the 2 right here. It's double angle. So now let's do a few problems where we're doubling the angle. So this is the first example, example 1. So let's do, here's the prompt. If cosine alpha, this looks like the one that we did last time, is 12 over 13, and alpha is somewhere in between 3 pi over 2 and 2 pi, and then I'll say with, oh, it's just that one, I'm sorry. Okay, so if cosine of alpha is 12 over 13 and alpha is somewhere between 3 pi over 2 and 2 pi, then they want me to answer the first one, part A. What is sine of 2 alpha? Now, we don't know what 2 alpha is. I don't even know what alpha is. So all I know is cosine of alpha is 12 over 13, and alpha happens to be in quadrant 4. So let's make a little sketch here. This is 2 pi over, or 3 pi over 2, and this is 2 pi. And angle alpha is somewhere here in this quadrant. So let's draw a triangle there. Cosine is the adjacent over hypotenuse, and this opposite side here, if you use the Pythagorean theorem, is going to be 5. I put a negative sign with it because we're in quadrant 4. So now we can use the sine double angle identity. So let's go ahead and do that over here. Remember what it is, 2 sine alpha cosine alpha. This one you will have to have committed to memory for the exam. It's not going to be given to you, so you have to know this one. So what is sine of alpha? Look over there at the triangle. It's going to be negative 5 over 13. Cosine of alpha was given to us up here. It is 12 over 13. And then we can multiply all of this mess together to find the final answer. So 2 times 5 is 10, times 12 is 120. That's negative. And 13 times 13 is 169. All right, good. Let's try another one. So here's part B. This one's probably just, cosine 2 alpha. Okay, well, we're going to do something very similar. So let's use the cosine double angle identity. You can use any of the 3. So remember what they are. It's these 3 right here. You can use any of those in this one. So the cosine double angle is cosine squared alpha. This is the one that I'm going to use, sine squared alpha. This is just the most common one. So what is cosine alpha? Cosine alpha is what that one was given to us. It was 12 over 13, and we want to square that. So notice I squared cosine alpha because that squared is squaring the cosine. So cosine alpha is 12 over 13, and I'm squaring it. So now let's square sine alpha, which is negative 5 over 13. 12 squared is 144 over 169. That's 13 squared. This is 25 over 169. They have a common denominator. Take the difference. We're going to get 119 over 169. There we go. Good. Let's try the last one. So part C is tangent double alpha. Okay. So what do we want here? Well, let's use the tangent double angle, which is 2 tangent alpha over 1 minus tangent. Is it a minus? It's a minus tangent squared alpha. Let's go back and just double check our identity. Yep, it's a minus here. So what is tangent alpha? We have to look at our triangle, opposite over adjacent. So that's negative 5 over 12 there. So negative 5 over 12 is what we want to replace tangent with. So we'll say 2 negative 5 over 12 over 1 minus negative 5 over 12 squared. This is going to be a little bit of a pain to simplify, so let's be careful here. So this is going to be negative 10 over 12 in the numerator. That's 2 times negative 5 over 12. You just double the fraction. And this is 1 minus, let's see, 25 over 144. Let's get a common denominator. The 1 is just 144 over 144. And let's carry this down. Negative 10 over 12 reduces to minus 5 over 6. 144 minus 25, we just did that one. It's 119 over 144. And then let's flip and multiply our fractions here. So minus 5 over 6, 144 over 119. 6 goes into 144 24 times, so that's going to be, let's just carry it to the right. So negative 5 times 24 over 119. And 25 times 5 is 125, so this is 5 less than 125, so it's 120 over 119. There we go. Good. Okay, so that's the basics of using the identity in a numerical situation, just doubling an angle. Now, this isn't super helpful because angles like tangent of 45, we know what that is, but if I double this, we already know what tangent of 90 is. What about tangent of 30? Well, we know tangent of 30. What about tangent of 60? Well, we know what tangent of 60 is. That's pi over 3. So we know all of those angles, and doubling them doesn't really help us. So where is this useful? This is useful in situations like this, where the angle is not given. So if the angle alpha is not given, but the ratio is known, and maybe the quadrant is known, you can kind of work around knowing the angle and finding double the angle. Okay, well, let's do some proofs. So this is example 2. These really aren't proofs, that you're just verify the identity. Okay, so here's part A. Let me give you an identity here. So how about this one? Tangent alpha is really the same thing as 1 minus cosine 2 alpha over sine 2 alpha. Do you believe it? I don't know. You probably do because I'm giving it to you. But we should probably verify that it's true. So pick the ugly side and rewrite it. My alphas end up looking a lot like 2's. Notice that? It's a little bit troubling. So you have to be very careful that your 2's and alphas don't get mixed up. So sine 2 and then alpha. I'll make my 2 a little bit taller than my alpha. There we go. So now the only thing that I can think of to do is to replace using the double angle identity. So, but the question might be, which double angle identity do I replace with? For cosine, we have 3 to choose from. Ugh. Well, which one would be the best choice in this case? We're trying to get to tangent alpha, so it would be nice to have sine in the numerator. So let's go back and choose the cosine double angle identity that has sine in it right here. So I'm going to replace the cosine 2x, or cosine 2 alpha, with 1 minus 2 sine squared alpha. So let's do that. So I'm going to replace this with 1 minus 2 sine squared alpha. So this right here, let's maybe draw attention to it. I'm going to put it underneath a squiggle line and say cosine 2x double angle identity. Okay, so that was a weird substitution if you didn't follow there. Notice that I put parentheses around it too, because we're not just subtracting 1, we're subtracting the entire cosine to alpha, which is this identity here underneath the squiggle. A sine to alpha, that was the identity that I really enjoyed in high school. That's the one that I remember really well. It's just 2 sine alpha cosine alpha. Let's see if we can simplify. The numerator here will distribute this negative to each of the two terms. So this is going to be 1 minus 1 plus 2 sine squared alpha all over 2 sine alpha cosine alpha. The ones wipe out. That's nice. That at least leads me to believe that I'm going in the right direction. So this is sine squared. 2 sine squared alpha is left in the numerator over 2 sine alpha cosine alpha. These are multiplied. One of these sine alphas is going to wipe out. So I crossed off the squared. And notice that the 2 out in front is going to wipe out as well. Those are both common factors. So those are gone. I'm left with a sine alpha in the numerator and a cosine alpha in the denominator. Sine over cosine is tangent. I think that was what we were trying to get to. Let's go back and look. Yep, we wanted to arrive at tangent. There we go. That's a pretty clever little identity there. Now, could you have done this problem if you replaced with a different identity here? Maybe you used cosine squared minus sine squared. If you did that, that would be fine. You might end up getting stuck at some point and having to use the Pythagorean identity, sine squared plus cosine squared equals 1, to help you get out of it. So you could have done that, but I don't think that would be the quickest way to get there. Could be wrong. But okay, let's try another one. So this is part B. So cotangent of 2 alpha is equal to, let's see, cotangent squared alpha minus 1 over 2 cotangent alpha. Interesting. So this is a cotangent double angle identity, which is not worth committing to memory. The tangent one, for heaven's sakes, isn't even worth committing to memory. So why would we commit this one to memory? What we will probably do here is start with, this one is an odd one. I think, honestly, I would start with the left-hand side, the easy side, the nice-looking side instead of the ugly side. Oh my, how do I explain that one? Perhaps explaining it would just be showing. So let's write this as cotangent 2 alpha, which cotangent is the same thing as 1 over tangent. We'll keep the angle the same, 2 alpha. And then we have an identity, the double angle. So this is why I chose to start with the easier side, or the nice side, instead of the ugly side, is because then I saw that I could use the tangent double angle identity here. What is it? The cotangent double angle identity, is this really going to help me? I don't know. We'll see. This is going to be 2 tangent alpha over 1 minus tangent squared alpha. And I think we're going to have to flip and multiply here. Will that do it for us? Maybe, maybe not. So let's flip and multiply. That doesn't quite look like what we're trying to get to. What do I do now? Let's multiply by 1 over tangent squared. multiply by cotangent squared. Let's try that. This is a pretty sneaky move. I don't know that this is the direction I've taken it here is perhaps the best direction. I'm not looking at notes as I do this. Let me look at see what I did here in my notes. I started with the ugly side in my notes, which probably would have been fine. Whoops. So what I'm going to do here is a little bit sneaky. I'm going to multiply by cotangent squared. Why am I multiplying by cotangent squared? Well, because I want cotangent squared. So I'm trying to be sneaky and get to the answer. So I'm looking at the answer to help me get there. So here we want to distribute this cotangent to each one of these. So this is going to be cotangent squared alpha minus tangent squared alpha times cotangent squared all over 2 tangent alpha times cotangent squared alpha. Well, let's replace the tangent squared alpha and cotangent cancel because cotangent alpha is 1 over tangent alpha, so they are reciprocals. They cancel, so those are gone. So this is going to be cotangent squared alpha minus 1 over 2 times, let's rewrite this as 1 over tangent squared alpha, so we can see the cancellation happening with this one. So then one of those cancels, which leaves me with cotangent squared alpha minus 1 over 2 times 1 over tangent, which is cotangent. So oof, that was a roundabout way to get there. There might be easier or better ways. Perhaps starting with the ugly side would have been better. Let me kind of hold it here. You can pause the video and kind of follow that work that I went through there. Maybe try, if you want to pause the video and try going another way, maybe try starting with the ugly side, so cotangent squared alpha minus 1 over 2 cotangent alpha, and then start by dividing both sides by 2 cotangent alpha. Yeah, and then you'll get some cancellation. Maybe that's a good direction to head, and you might be able to arrive at the tangent double angle identity. Eventually, you're going to have to get to the tangent double angle identity to help you. I'm not sure if this way is better. Either way, this one's going to be hard. Let's try another one. Let's try one that's maybe a little easier here. So here, this is part C. So cosine 2 alpha. Let's use a different letter than alpha. Let's maybe use cosine let's use a different Greek letter. How about we use gamma? There we go. Why not? So here's cosine 4 gamma minus sine to the 4th gamma. Whoops, I put in an alpha. Gamma is like a alpha that's turned upside down or turned facing downward. This is like a 4th cosine double angle identity. They're everywhere. So here's another thing that cosine double angle is equal to. Let's choose a side. I don't want to start editing right away, so let's choose a side to start with. I'll choose the right-hand side because it looks uglier. So cosine to the 4th gamma minus sine to the 4th gamma. Let's use a difference of squares. So cosine squared gamma minus sine squared gamma, and then we'll do cosine squared gamma plus sine squared gamma. So that's difference of squares. And this, of course, is our Pythagorean identity. So that's 1. And then here we're left with cosine squared gamma minus sine squared gamma, and that is one of our double angle identities. So this is cosine 2 gamma, which is what we are trying to arrive at. There we go. Very good. So, I mean, this is a short little lesson here using double angles. If you would like some more practice with this, your homework is worksheet number 7. So definitely check that out. And also page, it should be up on the board for you in class. If not, it's page 352 through 353. And you want to do numbers 1, 5, and 63 and 65. So that's just four bookwork problems there for you to attempt. But there we go. So hopefully we can talk about this more when I get back to class. We will have a review day. Let's see, so next class, and then we'll have the Unit 5 test. After the Unit 5 test, we have 2 midterm review days. So we'll review for the midterm, and then we have the midterm right before we leave for winter break. So this is the road to winter break here. So hang in there. Try to get this worksheet done. I am also adding another math space. So math space Unit 5, Day 3. This is just more practice. So check that out and try to get that done so that we will have that for next class. I will see you guys hopefully soon.